Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at some Paper 1 topical questions on the topic of DC circuits for Cambridge A-Level Physics 9702. And once again, these questions are from the Papa Cambridge topical questions, which organizes these questions by topic. So it's a good tool, a good resource to use if you are studying for your A-Level Physics exams, or in this case, AS Physics topic by topic. And I'll leave a link in the description so you can get these questions and work with them to test your understanding of the topic after you've covered the basic concepts. And today's video will be covering questions 1181 to 1189. And these questions, like always, are based only on the multiple choice, but multiple choice can be quite tricky, even though we might think it looks fairly straightforward and it's only based on AS concepts. They can get quite tricky. So check out my crash courses if you feel like you need a bit more background on the concepts before you start answering these questions. So the first question here is 1181. It's from the March 2020 exam. It's question paper 1, variant 2, and it's question 36 from that paper. We are shown a circuit in the diagram, and we want to know the reading on the voltmeter using the other values that are given. So what I have is an EMF in my battery of 6 volts and an internal resistance, this dashed line, this rectangle around the battery and the resistor means there's an internal resistance of 0.1 ohms. The external load, the external resistance is 2 ohms, and we want to know what the voltmeter will read. So this is a simple series circuit. So the first thing I want to do with a series circuit generally is to find the current in the circuit because it's constant throughout. And so I know that the EMF of the circuit is going to be the potential drops along the internal resistance and the external resistance. And so this is I into the external resistance R plus the internal resistance little r, which means the current is the EMF divided by the sum of the resistances, which is essentially the total resistance because both resistors are in series. And this is the EMF of 6 volts, the total voltage essentially divided by total resistance, which is simply 2 plus 0.1, which is 2.1, and we get a current of 2.86 amperes. Now, we don't really have to calculate this first. We could have just derived one equation and do the actual putting in of values later on, but let's calculate the current. And then I know from Ohm's law that the potential difference across the resistor is the current through the resistor times the resistance of that resistor. And this is equal to 2.86 amperes times the resistance now only of the resistor, 2 ohms. We have to be careful about the resistance we use here. And this will give us 5.7 volts. So the EMF is 6 volts, but the lost volts, which is the potential difference across the internal resistance, would be the remaining 0.3 volts, since the 2 ohm resistor is only reading 5.7 volts, which is option B. And so that's how we can calculate the potential difference across just a resistor. Okay, so just remember that for resistors in series, they are potential dividers. Okay, and so that was the first question. Not too bad, good warm-up. The next question is 1182. It's from the summer 2020 exam. That's May-June 2020. It's question paper 1, variant 1, and it's question 36 from the paper. A cell of EMF E and internal resistance little r is connected to a resistor of resistance big R. A maximum power P can be dissipated in the resistor without overheating. We want to know the maximum value of E if the resistor does not overheat. Okay, so I need to first work with the things I know. I need to remember that my EMF is my current I into big R plus little r, the total resistance, because this is a series circuit. Once again, we have a circuit that's in series, and so the total resistance is the sum of the individual resistances. And what I need to then do is, well, write an expression of the power that is dissipated through the resistor R, because the power P is the power dissipated through the resistor, or by the resistor, the heat that's given off by this resistor when the current flows through it. So P is only for that resistor. Now we know that P power is the current through the resistor squared, I squared, times the resistance of that resistor, big R. So why am I using this equation and only using big R? Because this is the power dissipated only by the external load, or by this resistor, not by the internal resistance. And what this means is that this current I can be written as the square root of P over R. Okay, so basically I'm just rearranging the equation to make I the subject of the formula. Why would I do that? Because then I can take that expression for I and put it back into the equation for the EMF, which is what the question asks me for. What's the maximum value of the EMF? And the EMF is equal to, let's write the thing in brackets first, big R plus little r. And now I can write the expression for I, because I don't have I anywhere in any of these options. And so the expression for I is the square root of P over R. So if I knew the values of the resistances, if I knew the power dissipated through the resistor and its resistance, I can find the maximum EMF the circuit can allow for the resistor not to overheat. And this corresponds with option D. R plus little r times the square root of P over big R. And so this is how we would go about it. We need to use the Ohm's law expression, E is equal to I times the total resistance, and then the expression for the power. So I needed to know two expressions here. The power expression is always important, especially the power through a single resistor. Always I squared times R, where I is the current through that resistor and R is the resistance of that resistor only. Okay, so that was the answer there for that question was option D. The next question is from the summer 2020 exam. It's question paper 1, variant 2, and question 36 from that paper. A cell of EMF E and internal resistance 0.5 ohms is connected to a resistor of resistance 4.7 ohms. The maximum power that can be dissipated by the resistor without overheating is 0.5 watts. What is the maximum value of E for the resistor not to overheat? Wait a minute. These are from two question papers in the same year, but different variants. And so these questions, as you can see, are identical almost, besides the fact that 1183 actually gives us values. So what I'm going to do is, well, if you're watching this question for the first time, remember that the total current is the total voltage, essentially the EMF, divided by the total resistance, which is again from Ohm's law, meaning the total EMF, I could have just written this down, is I into big R plus little r. And the total power through the resistor is the current through the resistor squared, I squared, times the resistance of the resistor, big R. I'm going to use big R to label that resistance and little r to label the internal resistance, and the current flowing through the series circuit I'm going to call I, just for clarity. And what this means is that this current can be written in terms of the power and the resistance as the square root of P over R. A little bit of algebra like I did in the previous question. What this means, therefore, is that I can write the EMF as big R plus little r, as we did before, nothing has changed, times I, which is now the square root of P over R. Because I'm given the power, but I'm not given the current. So I could calculate the current and then put it into this equation. It would work out to the same thing. But I'm doing everything in one go to reduce the amount of errors I will carry forward. And so this is the total resistance, which is 4.7 ohms plus 0.5 ohms times the square root of the power, maximum power being 0.5 watts, divided by the resistance of 4.7 ohms. And what I should get here for the EMF is 1.7 volts. So almost identical to the previous question, this gives us an answer which is option C. And the EMF, the maximum EMF that we can have with the resistor not overheating is 1.7 volts. So two things I had to do: Ohm's law for the equation relating current to EMF, and then the power equation for the power related to the current and resistance dissipated by a resistor. And so that's important that you understand those two concepts when having to calculate things like current or EMF and so on. Okay, the next question is 1184. It's from the summer 2020 exam. It's question paper 1, variant 3, and it's question 37 from the paper. We're told that a fixed resistor and a variable resistor are connected in series with a cell that has an internal resistance as shown. The graph shows the variation of a quantity X with the resistance R of the variable resistor as R is increased from 0 to its maximum value. And we want to know what could be represented by X. So we've drawn a graph of something against resistance that's increasing, but the rate at which it's increasing decreases gradually. And we want to know what increases with the resistance. Is it the current, the EMF, the potential difference across the internal resistance, or the terminal potential difference across the cell? Okay, so this is a little bit of a challenging question. It's one of those ones that require a little bit of work. So I'm going to label the internal resistance little r. I'm going to label the fixed resistor R1, and then obviously the variable resistor R. And then the EMF I'm going to label E, just to try and do some mathematics to try and figure out what can be on the y-axis. Now the total resistance in this circuit, R total, is all of these resistors are in series, so I can just add them up. It's R1 plus big R plus little r. Also, another thing we know here is that the EMF is constant. We always assume that our EMF is constant since for the duration of the experiment there isn't any loss of chemical potential energy within the battery, within the cell. And so immediately we can see that doesn't matter what I'm doing with the resistance, the EMF is not going to be affected by the resistance, so we can already eliminate option B. It's not the EMF changing with the resistance, it must be something else. Now the current in the circuit I is the EMF, and this expression will come to a few times, the one for the resistance. The current is the EMF divided by the total resistance, R total. Now I'm increasing big R, R1 and little r stay constant. We assume they stay constant. So the total resistance increases as I'm increasing the resistance of the variable resistor as I go from left to right. And if I increase the total resistance, what this means is that from this expression, the total current will decrease. Kind of makes sense. If I have a higher resistance, I have less current flowing through the circuit. So immediately that also eliminates option A. It can't be A, because as the resistance increases, the current is decreasing, but this graph shows that whatever quantity is plotted on the y-axis or on the vertical axis is increasing as the resistance goes up. So we need something that as R increases, it increases as well. So it can't be A or B. Now, the potential difference, I'm testing option C now, the potential difference across the internal resistance, I'll call it V little r, V subscript little r, is the current flowing through the series circuit times the resistance, the internal resistance little r. But remember that the internal resistance little r is constant. Okay, that means as I increase the resistance, which I am doing from left to right, then what I'm doing is I'm decreasing the current, like I said before, but that also means that VR will decrease. The potential difference across the internal resistance will decrease because the current is decreasing and internal resistance is remaining same. The potential difference across it will have to decrease. So it can't be that because this again is increasing. So we've eliminated option C. So by the process of elimination, you have enough information to say that it should be option D, but remember that the EMF is equal to the potential difference across the internal resistance plus the terminal potential difference, which essentially is the potential difference across R1 and R. And guess what? Let's write this down. V terminal, the terminal potential difference is VR1 plus VR, Remember, they are both in series, so they are potential dividers. But also what we remember is that the EMF is constant. We are not changing the EMF. So what this means is that if I increase the resistance and I'm leaving the EMF constant, then like we said, VR will decrease. But if I'm keeping the EMF constant and I'm decreasing the potential difference across the internal resistance, that means V terminal must increase with the resistance. So the only thing that's increasing from all these options with resistance is the terminal potential difference, which is option D. So by the process of elimination, the terminal potential difference must increase, but I could even show that it does increase. Since the potential difference across the internal resistance will drop, but E must remain the same. If I'm keeping E constant and I'm making the first, and it's the sum of two numbers, and the first number is getting smaller, the second number must get bigger in order to keep E constant. So the potential difference across the terminal potential difference must be increasing. So X is representing the terminal potential difference across the cell. So a little bit of a tricky one. You didn't need as much working or as much writing as I did, but again, you'd have to start eliminating things one by one before you confidently choose an answer. Unless you see in a question that's almost identical to this. But my suggestion would be to always try and eliminate things that you know can't be an option. That means it gives you fewer options to choose from. Okay, very interesting question there. The next question is 1185. It comes from the March 2019 exam. It's question paper 1, variant 2, and question 36 from that paper. We are told that a cell of internal resistance r and electromotive force, or EMF E, is connected in series with a resistance R. The resistance and the EMF E remain fixed, and the internal resistance of the cell changes with time. Which graph best shows the variation of the current in the circuit with the internal resistance R? Okay, so there's a few options here. How does current change with internal resistance? For me, you know I like my mathematics, but for me, I always find the mathematics sort of comforting in a way, because if I see an expression, then I can understand what the shape of the graph is going to look like. So I know the EMF is equal to the current I into big R plus little r. And I want the current as a function of internal resistance. So I'm going to put the current on the left-hand side on its own. I is equal to E over big R plus little r. So assuming the internal resistance changes as we vary the current. So the internal resistance can increase or decrease. And what type of graph is this? Now I'm plotting a graph of I against R, not a graph of I against, I don't know, the log of R or something. So I can immediately see that this is going to be a hyperbola. So I'm already eliminating options C and D. It's clearly going to be option A or option B. What I don't know about the hyperbola, just yet, is what's the asymptote. But what I know is if I plot a graph of y is equal to a over b plus x, then in the denominator, whatever I'm adding to x will be minus the vertical asymptote. So the vertical asymptote in this case, since little r is my variable, the vertical asymptote is the thing that's fixed, and it's minus the thing that's fixed. It's minus big R. Okay, so what this means is if I were to sketch a graph, again, you didn't have to sketch a graph. You could immediately tell from here what the correct answer would be. But if I just quickly, for my own happiness, sketch a graph, my vertical asymptote would be here in the negative horizontal axis. So again, I'm drawing a graph of current against resistance. And so minus R is my vertical asymptote. So this graph would be a hyperbola. And the other asymptote obviously will be the horizontal axis. And this graph would look something like that. Wouldn't touch the horizontal axis like it's done in this case. I should draw this a little better. Again, it'll be a lot easier if you were to sketch this with pencil. But in this paper, you wouldn't be required to sketch, but this is what the graph would look like. And that corresponds with option B. So it's always easy to think, well, it's definitely going to be hyperbolic, so I should just immediately choose option A. But if you actually look at the expression, you'd see that the vertical asymptote has been shifted to the left. It's not the vertical axis. It's not the I-axis. And so it actually will cut the vertical axis. And so the graph corresponds with option B. So always good to do the mathematics to see what the shape of the graph would look like, as you should know what a straight line looks like, hyperbola, parabola, the basic types of graphs, sine, cosine, etc. The next question is 1186. It comes from the summer 19 exam. It's question paper 1, variant 1, and it's question 35 from that paper. When a battery is connected to a resistor, the battery gradually becomes warm. This causes the internal resistance of the battery to increase while its EMF stays unchanged. As the internal resistance of the battery increases, how do the terminal potential difference and the output power change, if at all? So they want you to test two things in this problem. One is how the potential difference, or the terminal potential difference, is going to change. Two is how the output power is going to change if the internal resistance goes up, increases. So let's draw this circuit, shall we? We have a cell with EMF E, and we have an external load resistor, one load resistor, which is a series with the cell. And then we have our internal resistance. We usually label little r. And we have a current I flowing through the circuit. Simple series circuit. So the EMF, like we know, is by Ohm's law, I into big R plus little r, because these two resistances are in series. Now, as the internal resistance increases, immediately I can see what happens. The current I will decrease. I can simply rearrange this equation and see that, well, let's do it, shall we? I is equal to E over big R plus little r. The EMF will stay constant. We're assuming that the battery doesn't lose any of its chemical potential energy, still supplies a constant EMF E. Big R is fixed. It's a fixed resistor. And so the value of I will drop when the value of little r increases, which makes sense. The higher the resistance in the circuit, the lower the current. But we know what the current's going to be, but they didn't ask us for the current. They asked us for the terminal potential difference. What is the terminal potential difference in the circuit? So the terminal PD, by definition, is the potential difference across the external load, across the resistance R. That's simply I times big R. But I is going down, R remains constant, so terminal potential difference will decrease. What about the power? Well, the power is I squared R. This is the power, the output power, the power through the resistance. The output power will be I squared times R. And this will decrease as well. So the terminal PD decreases and the power decreases, the output power decreases. And so this corresponds to option A. So concepts that we've covered in previous questions, but always think about mathematical expressions to relate the EMF to the current to the resistances, and then the same thing for power. How do I relate the power to other things? And be able to do this for series, but also parallel circuits as well. Okay, that was option A. The next question is 1187. It's from the summer 2019 exam. It's question paper 1, variant 1, and question 36 from that paper. We're told that a cell is connected to a resistor of resistance 3 ohms. The current in the resistor is 1 amperes. A second identical resistor is added in parallel. The current becomes 1.93 amperes. What are the EMF and the internal resistance of the cell? Okay, so this is quite a complex question. I'm going to have to just remove everything else because we're going to need some space for this question. Okay. So they're asking us for two things here. And I mean, usually if they ask us for two things, then it's more likely, highly likely, also they give us two pieces of information. They gave us one piece of information for the single resistor and then another piece of information when we add another resistor in parallel. So what it's telling me, and also since there's two things required, it's telling me almost immediately that I'm going to have to solve simultaneous equations at some point. Maybe there's some other clever way of doing it, but I'm pretty sure you're going to be having to solve a system of two simultaneous equations in order to get an answer for this. So a little bit more of a challenging question. So I'm going to draw what the circuit looked like initially, and then I'm going to draw what the circuit looks like finally. And then looking at those two circuits, I'm going to put together, try to create mathematical expressions for the different quantities. So there's an EMF, E. So this is what the circuit was initially. So I'll say first circuit. And there was a current flowing through the circuit. I'll call it I1. There's the external resistance, big R, internal resistance, little r, and the current is constant in the series circuit. And let's then draw the second circuit. And so the second circuit looks, at the top at least, very similar. There's a cell connected to a resistor. There's an internal resistance of the cell. And there's a branch that looks identical to the first circuit that we've drawn. We have little r, which is the same, E is the same, big R also the same. But then we have a second resistor in parallel with the first. But it's identical, so it has the same resistance, big R. And now I have a current that breaks up. I'll call that current the one that breaks up I2. It splits. Who knows how it splits? But it splits. But the total current in this parallel circuit is I2. So from the left-hand side, what can we see? Well, I can see that the EMF E, which is constant, is I1 into big R plus little r. I'm assuming big R and little r stay constant. Now, putting my values in, I get big E is equal to 3 plus R. Why am I doing this? Because initially the current is 1 ampere. So that's 1. The resistor is 3 amperes, and the internal resistance, we don't know, it's R. So I have an expression with two unknowns. It's the EMF that's unknown and it's the internal resistance that's unknown. Which are the two things I need to calculate anyway, which is fine. So that I'm going to label this equation 1. And I'm going to do the same thing for the second circuit. Now, the only problem here is I need to first find the total resistance because it's not as easy as in the first circuit. The total resistance is R times R over R plus R for the parallel combination at least. So these two resistors, big R, are in parallel with each other, and we can assume that parallel combination is in series with the internal resistance. So it's R squared over 2R, and you can do this for yourself, you can check for yourself, plus the internal resistance little r, which is a half big R plus little r. So this is the total resistance, and it's different from the first circuit. Now I can look at the EMF equation. So the EMF is going to be this new current, I2, times the total resistance, again using Ohm's law, a half big R plus little r, because this is the total current and this is the total resistance. And this is a half times 1.93 times 3 plus 1.93 times little r. And then we simplify this and we get the EMF, which is constant, equal to 2.9 plus 1.93 r. And guess what? I'm going to call this equation 2. I have another expression for the EMF and internal resistance. Well, that's exactly what I wanted. Because if I have two equations with two unknowns, I can solve them simultaneously and find the two unknowns, EMF E and internal resistance R. So what I do is I take equation 2 minus 1.93 times equation 1, and what I get is that minus 0.93e is equal to, I should have a negative number on the right hand side, minus 7.89 or rather minus 2.89, and this gives me an EMF E, which will be 3.11 volts. Now it's easy. I can take this value of EMF, I can put it into either one of these equations. I'll go to equation 1. In 1, what I get is internal resistance is 3.11 minus 3, and what I get is internal resistance is 0.11 ohms. So I've got the EMF that I wanted, and I've got the internal resistance that I wanted. Does it correspond to any of the options in the table? It does. It corresponds to option C. So there's quite a lot of things to be done there, but in this case you saw they gave you two pieces of information. They gave you the current twice, and they asked you for two answers. So I'm 95% sure if I see that I'm more than likely going to have to solve a system of simultaneous equations. So more than likely, I'm also going to have to put pen to paper and actually do a calculation. Unless you're comfortable doing something like this in your head, I would suggest writing it down. And so that's a bit of a mathematical problem, but also requires you, I think redrawing the circuit diagram is not totally necessary, but I would highly suggest it because it's very easy to make one small error, which then leads on to many errors, and you might find that your final answer shows up as one of these options in the table, and that's when you can choose the wrong answer based on confirmation bias. Okay, so that's the question 1187. Interesting question. The next question is 1188. It's from the summer 2019 exam. It's from question paper 1, variant 2, and it's question 35 from that paper. A cell with internal resistance is connected to a variable resistor R as shown. The resistance of R is gradually increased, and we want to know how the current and terminal potential difference across the cell will change. Okay, so again, once again, we said the EMF is equal to the total current in the series circuit times the total resistance, which is big R plus little r. We'll label the internal resistance as always little r. And so the current is equal to the EMF of the cell divided by big R plus little r. Now we're going to assume that little r remains constant, the internal resistance remains constant. And so that means if I increase the resistance of the external resistor, the variable resistor, then I'm going to have the current decreasing. They are inversely proportional, well, not directly inversely proportional, but as you increase one, the other one decreases. And so if actually, the resistance of R is decreased, not increased. So the variable resistor decreases, meaning the current increases, which kind of makes sense again. If I decrease the total resistance, I allow more current to flow, and so I increases. But I still have to figure out what's happening to the terminal potential difference. So the terminal PD is equal to the current in the circuit times the resistance R, the resistance across the internal or the external resistor, the variable resistor. And well, I can see that obviously if I decrease the resistance as I'm doing, then I'm going to decrease the terminal potential difference. And again, why is this so? Because let's just see, EMF is equal to I big R plus I little r. E remains constant. The EMF is not changing of the cell, but we said that the current is going to increase and the internal resistance also isn't changing. So this term goes up. If something is constant but is equal to something that is increasing plus something else, that something else must decrease. And that's I times big R, which is the terminal potential difference. And so the terminal potential difference decreases when the resistance decreases, and that is corresponding with option C. So the current increases, but the terminal potential difference decreases. So always go back to Ohm's law and write an expression for the EMF in terms of the total current and total resistance. And you'll be surprised how often this helps with these kinds of questions, especially when they ask you for how things change when you change a resistance or when you change a current or something like that. Okay, now the last question that we're doing for today's video is 1189. It's from the summer 2019 exam. It's question paper 1 variant 3 and it's question 34 from that paper. We are shown in the diagram a lamp that is connected to a supply through two switches. During repairs, an electrician mistakenly reverses the connections X1 and Z1 so that Z1 is connected to the supply and X1 to the other switch at Z2 as shown in the diagram. And we want to know which switch positions will now light the lamp. So if I look at diagram 2, I need to figure out how I'm going to move the switch. So in diagram 1, this is what the switch would look like initially. If I have the supply as is, then I have no current. And let me just maybe change color. And if I flip the switch so that X1 is now no longer, maybe I can just use, if I flip the switch X1 from Z1 to Y1, well, guess what? Now I have a closed circuit. Before I had an open circuit. Now I have a closed circuit. And because I have a closed circuit, I have current. And so maybe I'll just draw this in orange. Okay, so if X1 is in position Z1 and X2 is just staying where it is, on Y2 I have no current. But then if I flip X1 to Y1 and I leave X2 at Y2, I have current. And I could do the same for the other switch. So the two switches could be at different positions in a room, etc., which means I go to the closest one. If the closest one is X1, then I can flip that switch to get a current. And the same would happen with switch X2. But then we have diagram 2 where things start to change. Okay, so I need to make a current flow in the circuit. And remember, I'm flipping X1 to either Y1 or Z1, or flipping X2 to either Y2 or Z2. So my suggestion for this kind of question would be to draw all of the options that you have, A, B, C, and D, and see which one will actually light the circuit. Okay. Let's flip X1 to Y1, and let's see what happens. Do I get any current for X1 to Y1? So if I let X1 go here, and let's again just remove the connection X1 to Z1. Well, if I think about what's going to happen, I don't have the supply connecting to X1 at all. And so this is actually an open circuit. There's no connection to X1 or Y1. And irrespective of what I do with switch X2, there's no supply. So X1 to Y1 immediately means there's no current. Why is that a good thing for me? Because that already eliminates A and B. Irrespective of what I do to switch X2, A and B cannot be the correct answer. So X1 to Y1 is not going to work. Okay, so it's going to be X1 to Z1, but what's going to be the second connection? So as I have it now, as you can see, if I follow this path, I don't have a closed circuit. My circuit is open. There's a gap here that I need to fill. So the current is not going to flow because there's an infinite resistance with that gap. So I have to connect X2 somewhere. And where's X2 going to go? Well, if X1 can't go to Y1, it has to go to Z1. And that means X2, actually, let me write it down, X2 to Y2 also results in no current. And so what I essentially need is X2 to go to Z2, because then I have a path for the current to flow. So if the current were to flow in that direction, it does have a closed path to flow from the supply back to the supply. And so what that means, X1 to Z1 requires X2 to Z2. So essentially what you needed to do here is try the combinations out and see which one gives us a closed circuit in order for the current to flow from supply back to the supply after going through whichever switch it needed to. So this corresponds with option D. And so it really only required your knowledge of, well, how a circuit works when it's closed and doesn't work when it's open for current to flow. And the diagram was a little bit complicated, but again, was just trying to throw you off. But you can still light the lamp with this double switch. Even though it's connected in reverse, it would still work. It's just a bit more clunky. And so that answer was option D. And so this was the last question for this video. I hope these questions were helpful. As you can see, DC circuits takes it up a notch from where we were at the topic of electricity. Obviously, expect the two topics to be intertwined in your exam, but you need to know how the basics of electricity work before you can start working on DC circuits. As you can see, it's much more difficult and much more challenging. And you will definitely be given a few questions in the exam that will test your conceptual understanding of the topic. As much as your mathematical understanding must be strong, conceptually you need to understand the topic as well. So I hope these questions were helpful. I hope that you're studying hard for your exams and everything is going well. Please like this video if you found it helpful. Comment if you feel like there's something you need to say. Subscribe to the channel if you haven't already. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.